Alright, today we're talking about section 7.3, logarithmic functions and their graphs. So we're going to talk about defining logarithmic functions, graphing logarithmic functions, evaluating elementary logarithmic expressions, and then common and natural logarithms. Logarithm definition. There's a more compact notation for the exponent that 3 must be raised to in order to produce 9 as an output. This is called the logarithm base 3. The notation of this is log, L-O-G, and then subscript 3, and then a 9. Because 3 squared is equal to 9, log base 3 of 9 is equal to 2. So here we say we squared 3 and we got 9 back out, but this asks the question, log says, what did you raise 3 to get 9? We raised it to the second power. In general, if a to the y equals x, then log base a of x equals y. In other words, what did I raise a to get x? I raised it to the y power. These are the two different ways of writing the same relationship. A to the y equals x is called the exponential form, and log base a of x equals y is called the logarithmic form. So basically what we're saying here is that when you have a logarithm and you plug in a number inside a log, you're going to get an exponent back out, whatever the exponent was on the base to get the number x. How I like to think about it. Alright, so write the following equations in logarithmic form. So here it's not asking to solve, and there's nothing to solve for. We're given all the appropriate information. So we're going to rewrite this in logarithmic form. So I'm going to say log. So if this is a to the y equals x, then log base a of x, so log base a of x will equal y. So in other words, here I'm going to have log base 2 of 8 equals 3. What did we raise 2 to get 8? We raised it to the third power. Next we have, we're going to rewrite this 9, the square root of 9, as, we're going to rewrite that as 9 to the 1/2 power equals 3. So now I have a base and a power. So I'm going to rewrite this as log base 9 of 3. What did I raise 9 to get 3? I raised it to the 1/2 power. My little ones have just come inside. Hold on a second. Sorry about that interruption. Alright. One day, my kids will be at school again, and I'll be able to record in peace. One day. So now we have another situation where we have 7 to the negative second power equals 1 over 49. So 49 is 7 squared, moved to the bottom because of the negative exponent. So basically we're going to say log base 7 of, and then this is our number here, 1 over 49. So what did we raise 7 to get 1 over 49? We raised it to the negative second power. So next is one for us to write the following equations in exponential form. So now we're going to say base, if we took 8, so we're going to rewrite this as 8 to the power 2 equals 64. So what did I raise 8 to get 64? I raised the second power, so 8 to the second power gives us 64. Over here, it's very similar. We have to write our base first, so here we're going to have 64 raised to the 1/2 power equals 8. Basically kind of the reverse of this. And then we have log base 5 of 125 equals negative 3. So we're going to say 5 to the negative third power, that's my base, to the power equals 1 over 125. Right. Once again, there's nothing to solve here. It just wants us to convert from one form to the next. So two special bases that we'll be seeing a lot of. There are two bases of logarithms that have their own notation. First is base 10, which is called the common logarithm. We write just log x without a subscript. That means it's always base 10. The second base is e, which is called the natural logarithm. We write the natural log x. It means we're using base e. So we talk about e in 7.2 and how it occurs everywhere. Very, very useful. And also, you can see you'd write it this way because log base e, that just kind of looks weird. It's much easier to write it as ln. Logarithms of inverse functions. Earlier we said that y equals log base a of x was the equivalent of a to the y equals x. If we find the inverse function of f of x equals a to the x, we start by writing y equals a to the x and interchanging x and y. This means the inverse function of f of x is equal to a to the x is f inverse of x equals log of a base a of x. In other words, they're inverses, so one undoes the other. So if we compose them, we'll get x back out. Compose a function with its inverse. So here's some properties of logarithms. A to the 0 power equals 1 for any value of a greater than 0, so long as log base a of 1 is equal to 0. And a to the first power equals a for any a greater than 0, so as long as a log base a of a is equal to 1. This is because a to the x and log base a of x are inverse functions, so a to the log base a of x is equal to x, like we said before, and log base a of x to the x, log base a of a to the x is equal to x. So this makes a lot more sense for most students to look at it this way. What did I raise a to get a to the x? I raised it to the x power. Once again, when we were saying before, when we had like bases, so remember when we had a to the x equals a to the y, and we got x equals y, basically we were taking the log base a of both sides. Oops. And that kind of cancels down to x equals y. That's essentially what we were doing back in 7.1. So any logarithm, so we have our chart here, we have log base a of 1 equals 0, because basically a to the 0 equals 1. Log base a of a is equal to 1, log base a of a to the x is equal to x, and log base a of x, a to the log base a of x is equal to x. Log of 1 is 0, log of 10 is 1. Remember that understood 10 is there. You know, we don't write it, it's understood to be 10. Log base 10 of 1 is 0, log base 10 of 10 is 1, log, usually just say it as log, of 10 to the x power is equal to x, 10 to the log x is equal to x. Natural log is the ln, so ln of 1 is equal to 0. Basically, log base anything of 1 is equal to 0. Base, where the base is greater than 1. I'm sorry, when the base is not negative or equal to 1. The natural log of e is just 1. The natural log of e to the x is equal to x. The e to the natural log x is equal to x. This is a trick we use very often, e to the natural log of x. It actually works very, very nicely in lots of parts of math. It's a little bit beyond what we need to work. I think for some reason it just paused. I'm not entirely sure why. So evaluate the following. Log of 100. So basically it's saying what did we raise 10 to? So remember the understood base is 10. And so I'm just going to rewrite this as 10 to the second power, so it's easier to see that we get 2 back out. Here the natural log of e, I'm just going to rewrite this ln of e to the negative third power, so it's easier to use our inverse rule and just say it's going to be negative 3. What did I raise e to get e to the negative third power? I raised it to negative 3. Here we're going to say log base 3 of 27. This may be a little bit harder to see. You know, once again, you can rewrite it as log base e of e to the third. And so what did I raise 3 to get 3 to the third power? Raised it to the third. Also, an alternate way of working these is saying something like log base 3 of 27 equals an unknown y, and then saying 3 to the y equals 27, and then saying 3 to the y equals 3 to the third, and so y must have been 3. So that's another way of working it, like we would have worked it from this portion right here, would have been like from chapter, or from section 7.1. Here we're using our inverse rules. So I raise 4 to log base 4 of 7. That's just going to give me 7 back out. That's the easiest way to look at it. You don't actually want to find the log base 4 of 7 and then use that as a power of 4. That would be very not useful, unuseful. It's easier just to use a rule of inverses. We have the following: log base 2 of 2 to times the square root of 2. I'm going to rewrite this as a log base 2 of 2 times 2 to the 1/2, which will give me log base 2 of 2. And then we add the exponents to the 3/2 is what this is. And so what did I raise 2 to get 2 to the 3/2? I raised to the 3/2 power. Once again, you could put this in a format similar to like what I said before. You could say this is log base 2 of 2 to the times square root of 2, and say that equals y, and say 2 to the y equals basically 2 to the square root of 2. And you can work it the same way I showed previously, like we would in section 7.1. You'd still have to put this 2 times the square root of 2. That would still come out to the 3/2 power. And here we have log base of 1, 2, 3, 4, 5 of log base 1, 2, 3, 4, 5 of 1, 2, 3, 4, 5. Well, that's just going to be my, what did I raise 1, 2, 3, 4, 5 to get 1, 2, 3, 4, 5 to the first power? I raised it to the first power. And here, any base, the log of any base of 1 is just going to be 0 back out. It's just our rule. Also, if it's a little bit harder to see exactly what's going on here, you could always say I have an unknown, I have 1, 2, 3, 4, 5 to an unknown power equaling, we rewrote this as rewrote that, and then you'd say, well, to get the same base, this would be 1, 2, 3, 4, 5 to the 0 power. That's the same thing as 1. So y must have been 0. In other words, it's equal to 0. So if you get confused, you don't remember your rules, you can always fall back on the stuff we learned in section 7.1. Alright. So next it wants us to solve the following equation. So now we're definitely going to, so if it's not very useful in logarithmic form, especially if your x is on the inside here, turn it exponential form usually helps. So I'm going to write this in exponential form. So when I do that, I'm going to get 2 to the 5th power equals 16 to the x. So that's a little bit more familiar. We get the same base, and we're going to get 2 to the 5th power equals 2. Well, 16 is actually 2 times 2 is 4. 2 to the 2nd is 4. 2 times 2 is 4 as well. 2 to the 3rd is 8, so 2 to the 4th is going to be 16. So this is going to be so 4 all raised to the x power. So then my bases are identical. We can get this to be 2 to the 5 equals 2 to the 4x. So that means I'm going to have 5 equals 4x. So that means that I'm going to get 5/4 equals x for this one. So there's a couple ways you can do it. You can turn to exponential form, which is basically saying 2 to the 5th, and thing of that nature. You could rewrite this as some form of 2 to the 4x. You're still going to have to go to exponential form eventually, though, to solve this. This one right here, it's easier to get the bases the same. So I'm going to have, since my logarithm's up in the exponent here, I'm going to say this is equal to 7 squared. And so we can think of these as canceling, in other words, log base 7 of both sides. And we're going to get log base 2 of x has to equal 2. So if I raise 2 to the 2nd power, I'll get x. So that means 2 to the 2nd power is 4, so x is 4. And so 4 is our answer here. I mean, this is almost, you can just almost do this in your head. Now, for those of you who are using calculators, if you have scientific calculators, they have on it a log button and a 10 to the x button. They have a natural log button and an e to the x button. Now, some of them have the additional one where we have a caret function here. This caret function right here, in some calculators, they'll have an any base key. And so you can say any base, but once again, you'll be using scientific calculators. You won't be using a TI-84. I just use this because it has a nice display screen. So you have some calculators that will do any base, but most calculators only do log base 10. I can get this to focus. No, I can't. These computers inside these cameras decide what I want to focus on at any given moment. But it has an natural log button. It has a log button. Hit the second function, you'll get the power button. And then we're actually going to have to use that here. So we have log base 10, it's understood to be base 10, of 4x equals 1.8. So in other words, I'm going to say 10 to the 1.8 power has to equal 4x. So that means if I divide both sides by 4, 10 to the 1.8 all divided by 4 equals x. Here we're actually going to need a calculator because anytime you have a decimal power, unless it's something like a nice fraction and it's like a good square root or something like that, or fourth root or fifth root or something like that, it can be nicely done, but here it's easier just to go to your calculator. You can use any number of buttons to accomplish this, if I can get it to focus without glare. And you can say this second function 10 to the x and go 0.8. You want to see that? Oh, come on, stay focused. And then hit down. Say the whole thing divided by 4. Make sure that 4 is in the denominator. You don't want to put it up there with the power. So we said it was going to be 15.77. So you'd say approximately x is going to be approximately 15.77. And usually it'll tell you to round off at so many decimal places unless you want an exact form. In other words, it want this exact fraction right here. But usually it'll say round off to so many places in Hawks. Next we have log base 9 of 4x minus 5 equals 1/2. So that means 9 to the 1/2 power equals 4x minus 5. So that's going to give me 3 equals 4x minus 5. So that means 8, because I add 5 to both sides, equals 4x. So divide both sides by 4. We get 2 equals x, and we're done. Once again, once you solve for something, especially something like this, you can easily plug this in and say 4 times 2 minus 5. That's going to give you 8 minus 5, which is going to give you 3. And the log base 9 of 3 is going to be 1/2. So it checks out. Remember to always check your answers, especially if you're doing something new you haven't done in a while. Make sure that you're on the right track. Nothing's more frustrating to get halfway through your homework. Hawks really won't let you get halfway through your homework, but realize you haven't fundamentally misunderstood things due to the fact you haven't been checking your answers. It can be really frustrating. And frustration is the bane of all math students everywhere. Alright, so next complete the following table and graph. So here we're going to say log base 2 of x. So in other words, if we're going to say that we have y, we want to figure out y. So if we say log base 2 of 1, well that'll give us 0 back out, right? And log base 2 of 1/2, what do I raise 2 to get 1/2? That'll give me -1 back out. And then we have log base 2 of 1/4. What do I raise 2 to get 1/4? Raise it to the -2nd power. Log base 2 of the square root of 2, which is going to be to the 1/2 power. Log base 2 of 2, that's just 1. And log base 2 of 4 is 2. So here if I was going to graph this, this is my... And so we'd mark off 1 and 2. So here at 1/2 and 1/4, mark off -1, -2, +1, +2. So here we're going to have the points. So at 1/4 we're at -2 right here. 1/2 we're at -1. At 1 we're at 0. And at 2 we're at 1. And then at 4, which would be over here somewhere, this would be 2, this would be 4, 1, -1, -2. I always do this, but I just don't center my graph very well. Have it. and we get something that looks like this. Remember, it's the inverse of the exponential function. The exponential function is reflected along the line x equals y, and that function, where we had y equals 2 to the x, that was the graph that looked like this. So you can see how this is reflected across the line x equals y. Alright, so here this one's going to be very similar. And once again, it's easy to start out with 1 because the log base 1/3 of 1 is equal to 0. Then we're going to have log base 1/3 of 3 is equal to -1. Log base of 1/3, 9 is equal to -2 because I take the reciprocal and square it. And then we're going to say log base 1/3 of 1/3 is going to be 1, and then log base 1/3 of 1/9 is going to be 2. So this is going to be very similar to other graph, except it's going to be kind of in the other direction. And so we're going to be looking at 1 and 2. Alright. So, oops, I go all the way up. Oh, sorry. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, way out there. And so we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9. And down here we're going to have -1, -2, +1, +2. And so now we're going to graph our points. And we're going to get, as we plug in numbers like 1, we get 0 back out. We plug in numbers like 1/3, which would be over here, be at negative, which would be at +1, excuse me. So plug in 1/3, we get +1. And -1/9, sorry, not -1/3. 1/3, we get 1 back out. A 9th, which is right here, there's a 9th. It'd be up here, and then we'd start curving down. So in other words, at 3, we'd get -1 back out, and at 9, we'd get -2. So it's basically the other graph reflected across the x-axis. Once again, we had that original, the graph we had from section 7.1. We were to graph that. We would have had the reverse graph, and it would have been right here at 1. So that's what would affect across the line x equals y. I need to be better about putting my endpoints on, or my arrows on, saying it goes on forever. I need to throw that marker away. That's getting faded too fast. Hot pink. That'll work. Alright. So now I'm going to get to the section. Well, first we're going to go over what we just learned. So the graphs of f of x equals log base a of x for a is greater than 1. Graph the functions the following of f of x equals log base a of x. Follow the rules when a is greater than 1. The point 1 over a is equal to -1. You plug in 1, you get 0 back out. You plug in a, you get 1 back out. And will always be on the graph because the domain is from 0 to infinity. The graph can't go left to the y-axis. And because we can't plug in any negative numbers, because there's no power we can raise a positive whole number base to, or sorry, I shouldn't say whole number, and a positive base to, not including 1, that would give us a negative number back out. So in other words, for the domain, I can't plug in a negative number because that means I got a negative number back out when I raised a non-negative base to a power. In other words, I have my log base 2x here and my log base 3 here. And these will increase from left to right. And my range is going to be all real numbers, because your domain and the range switch from your exponentials to your logarithmic. And here is very similar. When my base, if I have f of x equals log base a of x for 0 is less than a, which is less than 1, the graphs of the following functions of the form f of x equals log base a of x. Follow these rules when 0 is less than a. and a is less than 1. The points a over 1 and -1, 0, 1, and a 1 will always be on the graph. Now once again, remember a is less than 1, so even though this looks like a fraction, it's not less than 1. This is actually a number greater than 1 right here. So when you plug in that fraction, you'll get a negative number back out. This is not a this is a number greater than 1, so it's actually over here, and you get -1 back out right here. And then because the domain is once again from 0 to infinity, can't go left of the y-axis, the graph will decrease from left to right. Alright, so now they want us to graph. So sketch the basic shape of the graph, determine the transformations necessary to obtain the graph from the function from the basics graph, draw the graph and write the domain in the range of the function. So for this, looking at it, we'll be looking at these 3 functions here. Remember, for Hawks, all they really care about is getting 2 points so you can match it to the graph. They don't have you graph an entire one freehand, but for us, we're going to be practicing that, and that's when your transformations come in super handy. So, in other words, we have a log base 2. Oh, also on these, you may see them described as graphing the exponential and reflecting across the line x equals y. It's another way you can graph these. But here we're going to say we have our basic graph, so let me draw the basic graph up here. So this is going to be a log base 2 of a number. So log base 2 of a number is going to look something like this. All right. So I cross the x-axis at 1. Now, -5, if I subtract on the inside, it's going to move what used to give me 1, when I used to plug in 1 and get 0 back out. Now in order to make this 1, I'm going to have to plug in 6. So it's going to move over right to 5. 1, 2, 3. So I'm going to be over here at 6. So that's going to be my new graph. So that's just a rough sketch. So here we're going to, it's going to move 5 units to the right. And then, so for this, it's good to mark off some good numbers to plug in. So here are x values, here are y values, or our log base 2 x minus 5 values. And so, like I said, so before plugging in 1 would have been nice, but here if we plug in 1, that's not even defined for this. So, with this in mind, well, let me start over again. Let me say this is going to be the x values, this is going to be x minus 5 values, and this is going to be your log values, log base 2 of x. So here, I want this part to give me nice numbers. I want to be able to plug in 1 for this. So if I'm going to plug 1 in here, into this row, to get 0 back out for my log, this right here is going to have to be 6, because I'm going to add 5. So it's 6, I'm going to have 6 minus 5 gives me 1. Plug in 1 into my log base 2 here, get 0 back out. Another good number that would be nice, if this was 2, this was a power. So what I'd really like is inside here to be a power, a whole number power, or I should say an integer power of the base. I'll read that small. So if I get an integer power of the base to be inside here, like 1 is an integer power of the base, in other words, it's to the 0 power, then I can make nice things happen. So in other words, if I want to get this to be a 2, well, log base 2 of 2 is going to be 1. Well, if I was going to make that 2, this says, if I was going to minus 5 from that, or minus 5 from a number to get that, that would be 7. So in other words, here I'd have my graph. I plot out 2 points that I have really good points for. 1, 2, 3, 4, 5, 6, 7. I'm going to have 0 and 1. I'm going to have this graph. It's going to cross at 6, and then it's going to be 1 at 7. So it's going to have this, and it's going to have that. Remember, it's going to have that vertical asymptote. It's not going to be able to cross anything to the left of 5, because if we go to the left of 5, we'll get negative numbers inside here. So let me draw that line. Remember, this line flattens out pretty quick because it's exponential, it's logarithmic, so it grows extraordinarily slowly. And then we're going to say our domain. Since basically subtracted 5 from it, I moved it 5 units to the right, so this right here is a 5. It's going to be bounded to the left by 5 and go all the way to positive infinity. It's not going to, we can't plug in 5 because that would make this 0. 2 to no, there's no power I can raise 2 to get 0 power back out. And the range, well, I'm just going to get all real numbers back out because it goes down forever and it's going to eventually go up forever. It takes an extraordinarily long time to get to infinity. An infinite number of time, an infinite amount of time actually, but it'll eventually get there. So that's our range. So next, very similar, we have log base 3, what we have here. So our basic function is going to look like this once again. Then I'm going to add 3 to it, so it's going to move it back 3 units. So we're going to be back 3 units here. And then, well, let me do that in a different color. It's going to be back 3 units, and then what's going to happen to it is that I'm going to reflect it across the x-axis. So that actually is going to make it look like this. So that's what a graph is going to look like. So that's just a rough sketch. So let's keep track of things that we're going to do. We're going to move left 3 units. And then we're going to, so that's our first transformation, and our second transformation is going to be reflect across x-axis. And so in doing so, once again, we want to make this whole number powers of 3. That would be really nice. So we can make a couple of things here. We can have this be x, this be x plus 3, and this be log base 3 of x plus 3. And you can make it negative right there if you like, right off the bat. That's fine. And so we want this to be whole number powers of 3. So what would give me whole number power of 3 here would be 1. That would give me 0, negative 0 back out, which is still 0. And then, so that means the original x had to be what? So if this, I had to add 3, this would have to be negative 2. If I want this to be a power of 3 in this column, so 3 is a power of 3. So that means over here, if I plug in 3, right here, log base 3 of 3 is 1. That would make it negative 1. So what would give me 3 here? Well, if I add 3 to it, I'm going to have to subtract it back off. So this must have been 0. So if I plug in 0, then I'm going to get negative 1 back out. So with those two main points, and you can graph other points, any powers of 3 could work. So if you had this middle, these are going to be powers of 3. We want these to be powers of 3. So I get 9. So that means it's going to give me log base 3 of 9 is 2. It's going to be negative because that negative out front. And then what happens here, I'm going to have to add 3 to get this 9. So that means to go back to x, I would have to subtract 3 from it, which would be 6. Alright, so let me graph this. Alright, so I'm going to plot off the points. I'm going to need negative 2. I'm going to need 0. I'm going to need 6. And I'm going to need negative 1 and negative 2. And so the points I'm going to plot is negative 2, 0. And then I'm going to plot off. I'm going to need 0, negative 1. And then I'm going to need 6, negative 2, which will be right here. So this is negative 1. And then over here, I'm also going to plot negative 3, because that's actually where my vertical asymptote is. I can't plug anything to the left of negative 3, because then my function is no longer defined. So let me draw this line. It'll look something like this. My domain is going to be negative 3 and all my numbers there, or all the way to positive infinity there, and then I'm going to have my range. I'm sorry, I move away from my mic when I'm writing on here. Once I get a better setup, I'll be able to have my mic directly over my head and I won't have to lean back to write on my paper. That is your domain and your range. So basically, we had this general graph, we moved it back 3 units, and then we reflect across the x-axis, and once again, that's what we got here. Alright, so here we have a fractional base, so that's a little bit more interesting. So we're going to have the basic graph. It's going to look something like this. So instead of increasing very slowly, it's going to decrease very slowly. Well, it's going to decrease rapidly here, and then it's going to be slow. So this will be your exponential right here. Sorry, your logarithmic right here. And so then we're going to subtract 5 from it, so it's going to move 5 units over. So this is 1. This will now move over to 6. It'll be right here. And that's the only thing we need. We just need to move to the right 5 units. Alright, so this is very similar to the one we did here, only you're going to see it's going to be reflected across the x-axis. We'll talk about that in a second. So let's set this up. So I'm going to have an x column, I'm going to have an x minus 5 column, and then I'm going to have my log base 1/2, sorry, x minus 5. So here I want powers of 1/2 would be nice. Well, 1 is a power of 1/2, it's 0. So if I add 5 to that, going this way, that's going to be 6. So I plug in 6, subtract 5, I get 1. 1 log base 1/2 of 1 is 0. And here, instead of plugging in something that would give me a power of 2, of 1/2, like 1/2, I don't want to plug in fractional numbers. So instead, I'm going to say I want this to be 2. Because if I plug in 2 to this, then I'm going to get -1 back out. Now what would give me 2 here is if I added 6, so this would be what? This would be 7. So I plug in 7, I'm going to get -1 back out. And so it's very similar to what we did before. We're going to get 1, 2, 3, 4, 5, 6, 7. I need -1. Here I'm going to need the point. Still see that? 6, 0, and 7, -1. Once again, label your points. Always -1 there. And we're going to have 1, 2, 3, 4, 5, 6, 7. And then remember, 5 is going to be that vertical asymptote right here. Because I can't plug in any negative numbers inside my logarithm. And if I plug in anything less than -5, or if I plug in anything less than 5, or 5 itself, I'd get an undefined number. And here would be this right here. Now, here's an interesting thing. So, if you look at this, alright, so let me do the domain and range before I get domain. Very similar to what we did before. It's going to be from 5 to infinity. That's where I can't plug in numbers anymore, x values. And the range, once again, is going to eventually get all my y and x values, -infinity to +infinity. Now, you notice that the number A and number C were very similar. They were just reflected across the x-axis. Well, if you look at it this way, I have that here. So if you look at this way, you can look at the fact that we have. No, we don't have change of base yet. Let me not do that. Let me cut that off. But yeah. This base is good basically if the log was negative of the original reciprocal of this. It's basically what it turns out to be. Can't really explain it without change of base helping me out there. So I might cut this part of the end of the video off. Y'all have a great day.